We're going to do a little piece of Chapter 19. This will also be taught in Chem 1B, but it's on our course outline for transfer to other schools that we cover what we're going to cover right now. So that's why I'm doing this. Okay, so we're going to talk about how to balance redox reactions. I don't know what's going on here. So this is a review. We just did this, so I don't think we have to go over this too much. Oxidation is loss of electrons, reduction is gain. We've got the increase in oxidation state or the reduction. When we balance a redox reaction, the masses have to balance in terms of we need the same number of atoms of each element, but we also have to make sure that the charge balances. And so in order to do this, we're going to break the equation into two, what we call half reactions, two halves. We're going to balance each half reaction separately and then add them back together. And this is the best way to make sure that the charges come out how they should. So that's a review of assigning oxidation states. Since we just did that, I don't think we need to go over that again. But here's the procedure for the half reaction method of balancing aqueous redox equations in acidic solution. Assigning oxidation states, identifying substances being oxidized and reduced. That's a good thing to do. If the question isn't specifically asking which is being oxidized, which is being reduced, we don't actually have to do that part. We'll do it for practice. We're going to separate the overall reaction into two half reactions. One will be oxidation, one will be reduction. We don't actually have to identify them, and that's why we don't have to do number one. So we're going to balance each of those half reactions for mass first. And here we're going to balance everything but hydrogen and oxygen, and then we're going to balance the oxygen by adding water, and balance hydrogen if we need to by adding hydrogen ions. And the reason that we're adding water or hydrogen ions is because we're doing this in an aqueous solution and it's acidic. There are hydrogen ions present. Then we balance each half reaction with respect to charge. So we need to make sure that the total charge on each side of the arrow is the same. It's not going to be zero necessarily, but it just needs to be the same. We're going to balance that by adding electrons to whichever side is needed. Electrons have negative charges. Then we're going to make sure that the number of electrons in both of the half reactions is the same number of electrons. And then we're going to add the half reactions together and double check that it's balanced. So start off with a relatively simple one, and here is the short list of the steps. So assigning oxidation states, so aluminum is going to be 0, and the copper here is +2, and the aluminum here is +3, and this copper is 0. The oxidation state corresponds to the charge on these ions, right? So we see that the oxidation is the aluminum being oxidized to Al3+, copper is being reduced. We have two half reactions, and usually we have two reactants, and so you pick one of them. I'll start with the aluminum because it's first. And so I'm going to put, I've got aluminum, it's a solid, and that's going to react to form. Now I want to pick the product for this half reaction that's got aluminum in it. I can't have aluminum metal being changed into copper metal. That doesn't happen. So it's the aluminum ion that's going to be over here. So that's one half reaction. The other half reaction will be the other reactant, as Cu2+, and the copper over here. So this is our oxidation reaction, half reaction. This is our reduction, half reaction. So I've got steps 1 and 2. Now I need to balance these with respect to mass. Well, I've got one aluminum here and one aluminum there. So that's already balanced for mass. And the other one, I've got a copper ion, a copper atom. They're balanced for mass. But the charges aren't balanced, right? Because when we look at this overall reaction, on the left side I've got a total of a positive 2 charge. On the right side I've got a total of a positive 3 charge. An electron went missing. That's not possible. And so this reaction isn't actually balanced, even though it kind of looks balanced. So aluminum going to aluminum 3+, I need to balance that so the charges are the same on each side. And I'm going to do that by adding in electrons. So this side's positive 3 and that side's 0. If I add 3 electrons to this side, I've got 3 -1 charges. Now those charges add up to 0, and on the other side I've got 0. Does that make sense? This one, I've got the positive charges over here, and so that's where I need to add the electrons. I need 2 electrons. I need the charges to be the same on each side. Everybody okay with that? So step 5, make the number of electrons equal. Well, I can't change a 3 into a 2 or vice versa, but I could change each of them into 6, right? Let's change colors here. So if I multiply this reaction by 2, that'll give me 2 aluminum atoms, 2 aluminum ions, and 6 electrons. Still balanced. I just multiplied everything by 2. And this one I'm going to multiply by 3, and so that's going to give me 6 electrons, and 3 copper ions, and 3 copper atoms. The reason I want to get the number of electrons to be the same is that when I add this reaction to that reaction, I've got 6 electrons over here, I've got 6 electrons over there. The 6 electrons that are produced by the first half reaction get used up in the second half reaction. The electrons are transferred directly from one thing to another thing. You can't just have extra ones left over, and you can't pull extras in from somewhere else. That's why the number of electrons has to be equal. Then I'm going to add these together. So those 6 electrons will cancel these 6 electrons. They got made and they got used up. So those got made and used up. Nothing else. That's a lot like canceling out spectator ions. Nothing else is canceling out though. So I'm just going to copy down what I've got left here. Got 2 aluminum solid plus 3 copper 2 plus aqueous, forming 2 aluminum 3 plus ions plus 3 copper atoms. The difference between our starting equation and our final equation is our final equation is balanced for charge as well. We look at the total charge on the left side, 3 times 2, positive 6. Here we look at the total charge on the right side, 2 times 3, positive 6. This was not balanced for charge. Any questions? Let's do another one. So here we've got hydrogen ion and chromium atoms making hydrogen gas and chromium ions. I'm going to skip the first step. It's a nice step, but it's actually not necessary. So I need to separate this into 2 half reactions. Well, let's start with the H+. So one of the reactants there, the other reactant here. So if I've got H+, then I look at my products and say, well, which one is the closest, the most similar to H+? Well, it's the H2, right? It's got to have the same elements in it. And Cr2+ must go down here. So I can change chromium into chromium ion by messing around with the electrons. I can't change chromium into hydrogen gas. Okay, so I've got my half reactions, balance it for mass. So this top one here, I've got 2 hydrogens on the right side and only 1 on the left. So it must be 2 hydrogen ions. And down here I've got chromium atom, chromium ion. That's already balanced for mass. Then I balance with respect to charge by adding electrons. So up here I've got 0 on the right side and I've got +2 on the left. So I can add electrons. I'll add 2 electrons. And so now I've got a total of 0 charge on the left and 0 on the right. Down here, how many electrons do I need? I need 2, and should I put them on the right or on the left? I'll put them on the right. 2 electrons here, because that's where the extra positive charge is. So we've balanced these 2 half reactions. What we've got here is this one is gaining electrons. This is the reduction half reaction. This one we're losing electrons. That's the oxidation half reaction. We need to make sure that our numbers of electrons are the same. This time they are. There's 2 there and 2 there, so we don't need to multiply. We can just add these together. The electrons should always cross off, just like spectator ions cross out, and then we write down what's left. We got 2H+ aqueous plus Cr solid, making H2 gas plus Cr2 aqueous. Double check that it's balanced, and there you go. Any questions? Yes?
Why were we adding hydrogen ions with respect that we had for respect to mass?
So why did we add a hydrogen ion here?
No, never mind. I was reading this.
Oh, this part, yeah. So that happens. Sometimes we've got something in here and we can't balance it. We can't balance the hydrogens without just flat out adding some. So we'll see an example of that. Oops, I skipped one. Okay, let's do this one. Now we don't have our cheat sheet notes on the side. So we need to separate this into 2 half reactions. So I got the iron here, and then I've got this one with manganese, and there's manganese over there. So I can just kind of eyeball it and see which 2 things go together. I just tend to put the first one in the first and the second in the second, but it doesn't matter. And then the other reactant that's permanganate ion. And that's going to go to Mn2+. Next step is balancing by mass. So the first one is fine. The second one, the manganese, is balanced, but I've got oxygen over here and there's no oxygen over there. We're going to balance the oxygen by adding water molecules. All of this is occurring in aqueous solution, so there are water molecules. It's not like we're making anything up. So I'm going to add H2O so that I can balance the oxygen here. If I have 4 oxygens there, I need 4 water molecules on the right side. So that took care of the oxygens, but it introduced another problem. Now I've got hydrogen in here. It wasn't there before. This is where we balance the hydrogen by adding hydrogen ions. We add hydrogen ions. This is an acidic solution. In an acidic solution, we have extra hydrogen ions. So I'm going to add H pluses over here. How many do I need? 8. I need 8 because each water molecule had 2, right? So 8 hydrogens. So now I've got the correct number of letters on each side. Now I'm going to balance charge using electrons. So here I've got +2 and +3. If I add 1 electron to the right side, then both sides are +2. They just need to be the same on both sides of the arrow. It doesn't have to be any specific number. Now this one's getting a little more complicated. We need to be careful here. So we have +8 and -1. So total on this side's +7, right? And over here I've got +2. So I need to make this smaller. I'm adding electrons. So if I got +7 and I want +2, I need 5 electrons. It's easy to make mistakes when you do that in your head, so feel free to actually write it all down. Now I need the same number of electrons on each side. So I've got 5 on this one and 1 up here. So if I multiply the top reaction by 5, then I'll have 5 electrons on both sides. So I'm going to get 5 Fe2 pluses, 5 Fe3 pluses, and 5 electrons. Now that I have my electrons the same, I can add these back together. I think of the 5 electrons as being spectators. They're just transferred from one to the other, and so they don't show up in the final reaction. So I've got 5 Fe 2 plus aqueous plus 8 hydrogen ions and 1 permanganate ion. Forming 5 iron 3 ions plus manganese 2 ion plus 4 water molecules. This one's going to be hard to balance by inspection, right? The regular way we've been doing, because you've got oxygen here and there's no oxygen over there. So the half reaction method is definitely the way to go for something like this. Any questions?
Does it matter what order we write it in? Like,
No, it doesn't. It's a good question. So does it matter if you put the Fe2 plus first or the H plus first? No, it doesn't. Because just like in math where 2 plus 3 or 3 plus 2, the order doesn't matter. The order doesn't matter here. I tend to do it just in the same order as it was presented, but it doesn't matter at all. Any other questions? I'm going to skip that one. What if we have a basic solution? So if we're balancing in basic solution, we do the same thing as for the acidic solution, but we add a step at the end. Well, not at the very end. We add a step here where we're balancing by mass. After you've balanced everything, then we've got a basic solution. So any of those hydrogen ions, we're going to add an equal number of hydroxide ions to both sides of that equation. I'm going to do this one. So balancing a redox equation in basic solution. So we're going to do the half reactions. And you should be able to look at these and identify that, okay, these two go together. They both have chromium in them. And this one goes with that one. They both have chlorine. And so that's how you decide what's in the first one, what's in the second one. So I've got that hypochlorite ion going to chloride ion, and then I've got this complex ion. going to chromium, or chromate. How I got so, well, we'll make it work. Balance by mass first. So 1 chlorine and 1 chlorine, that's okay, but here I've got an oxygen. You balance oxygens by adding water molecules. So I'm going to add H2O to this side. So now I've got an oxygen on each side. Then I balance the hydrogens by adding H+. So I've got 2 hydrogens here, so I have to add 2 H+ to that side. Because this is in basic solution, the next thing I'm going to do is I'm going to look at these H+. I have 2 hydrogen ions here. I'm going to add 2 hydroxide ions to each side. So it's still going to be balanced. So I'm going to add 2 OH minus and 2 OH minus. That's because this isn't an acidic solution, it's in basic solution. Hydroxide is the base. So when I have 2 hydroxide ions and 2 hydrogen ions, what does that make? Water. Makes 2 water molecules. So I can simplify that and write 2 water molecules there instead. Now, if you want to, you can go ahead and say, well, I got 2 water molecules there and 1 over there. I could simplify that further, or you can just leave them alone and take care of it at the end. I'm just going to let it go till the end. Let's look at the charges now. On this side, total of -1. On this side, a total of -3. I've got 1 here and 2 negatives there. So that tells me I need 2 electrons over here. Any questions yet? So let's look at this one down here. So there's chromium and chromium, so that's okay. Got 4 oxygens and 4 oxygens. Wow, this is going well. 4 hydrogens. How do I balance the hydrogens? Add hydrogen ion. So I need to add hydrogen ions, 4 hydrogen ions to this side, to balance the mass. But it's in basic solution, so then I've got 4 hydrogen ions. I need to add 4 hydroxide ions. And this I'm going to do to both sides because I had it mass balanced and I don't want to screw that up. Four hydrogen ions and 4 hydroxide ions make 4 water molecules, right? So I'm going to erase those 4 water molecules. Then we have to look at the charges. I've got 4 negatives here and another negative, so a total of -5. And over here I have -2. So I need to add 3 electrons over here. You should always end up with electrons on the reactant for 1/2 reaction and in the product for the other. If that's not happening, something else is wrong. What's the next thing I need to do? I need to make balance the electrons, make the electrons the same, right? I've got 2 in this half reaction and 3 in this half reaction. I need there to be the same so that they're going to, cancel each other out. So I'm going to go for 6. So I'll multiply this top one, where I have 2 electrons. I'm going to multiply this by 3. So I get 6 electrons and 6 water and 3 of that ion, 3 of this ion, 3 of H2O, and 6 of the hydroxides. It's still balanced. I'm just multiplying all the coefficients by the same number. take this bottom one, I'm going to multiply by 2, because if I take 3 electrons and multiply by 2, I'm going to get 6 electrons, and that's the goal. So multiplying by 2, I get 8 hydroxides, and 2 of those ions, and 2 of these ions, and 8 water molecules, and 6 electrons. And we're going to add things together. So I've got 6 electrons in the first one on the left and 6 electrons in the second one on the right, and so those are going to cancel out. You can simplify, we've got water and hydroxide all over the place as well. You can simplify that now, or you can simplify it after you add everything together. I'm just going to add them together, and then we'll simplify it. So I've got 3 ClO minus, and I've got 6 H2O, and I've got 8 hydroxides, and I've got 2, that's not a 2, CrO4 minus, aqueous. Did I miss anybody? And now it doesn't look like this is going to fit on the next line, so I'm going to drop it down. I've got 3 chlorides, and here I've got 3 H2O, and down here I have 8. Let's combine those together. It's 11 water molecules, and there's 6 hydroxides, and 2 chromates. Okay with that? You got to copy stuff down carefully. Now let's look at this and make sure that we don't have duplicate stuff, which we do. I have 8 hydroxides on the left side, and I have 6 hydroxides on the right side. So I could take 6 hydroxides off of both sides and have it still be balanced, right? So I'm going to take those 6 out, and I'm going to take 6 out from this side, which makes that a 2. Subtracting 6 hydroxides from each side. I've got 6 water molecules on the left and 11 on the right. So I'm going to subtract that out as well. So I'm going to get rid of all 6 on the left. I'm going to subtract 6 here. That's going to leave me with 5 water molecules. And then I'm just copying down so it's a little easier to look at. And if you go through and check the charges and the number of atoms of each element, it should balance out just fine. Any questions?